All right. Good morning. And today we're going to be looking at a Deepmind paper that was super fresh, just released a couple days ago. And it's just here we go, 2022, 11/15. And it's called Controlling Commercial Cooling Systems Using Reinforcement Learning. So this is a bunch of people at Deepmind, Google, and then Train. I don't know what Train is. We can look that up. Train is a manufacturing company. Okay, so it's kind of like an HVAC company based in Dublin. Okay. This paper is a technical overview of their recent work on controlling commercial cooling systems. Okay. Building on expertise that began with cooling Google's data centers more efficiently, we recently conducted live experiments on 2 real-world facilities. Building management system provider. Live experiments had a variety of challenges such as evaluation, learning from offline data, and constraint satisfaction. Our paper describes these challenges in the hope that awareness within will benefit future applied RL work. Yeah, and these papers are always really cool. I think the other ones that's very similar to this is the Deepmind paper, where they used a reinforcement learning agent to magnetically levitate the plasma in a tokamak reactor, right? A fusion reactor. So I think there's a lot of these little problems. They're not little, but they're kind of these control problems that exist in the real world, and reinforcement learning is a very good tool for them. So I'm glad to see that Deepmind is kind of figuring out how to apply its reinforcement learning expertise to these real-world problems. Resulting in energy savings of approximately 9% and 13%. So, I mean, this is a little anticlimactic, I would say. It just kind of goes to show you that Train Technologies, right, and other HVAC manufacturers over the decades have, using their engineering and human kind of design, have been able to make these HVAC systems pretty efficient. So there isn't a huge amount of performance juice to squeeze out. Okay. HVAC, heating, ventilation, and air conditioning, if you ever were curious what that means. Okay, costs a lot of electricity, data-driven, autonomous, and real-time decisions. Improving efficiency. HVAC control is a decision-making problem with decisions including turning equipment on and off. Okay, so this is kind of the different actions of the system. You can either turn it on and off. You can adjust how hard to run each piece of equipment. There's a natural reward function, which is energy use, right? It's very easy. And then constraints, which is you want to keep a certain temperature. Another acronym for you here, building management systems. So I don't know what, apart from HVAC, that would include. Maybe it would also include, I don't know, cameras, doors locking and unlocking, maybe like allowing air to circulate between places by opening doors. Yeah, finally, unlike model predictive control. So this is where you build a model of your system, and then you use that model to find the optimal control policy for whatever you want to optimize in that model, right? And the problem with kind of HVAC in a large building is that your model for that system is not going to be particularly great, right? There's a lot of dynamics in there that are very difficult to model, and reinforcement learning is great in that you don't actually necessarily need this model to be very detailed and descriptive, right? Kind of RL can work in a somewhat black box environment. Although I would say that the tokamak was trained actually in simulation, so there is something to be able to simulate the system, and I'm curious in this paper to see how much simulation they actually use. Expensive and noisy data. Okay. Something they ran into. Different operating modes and multi-timescale dynamics. Yeah, so I think that's maybe the more interesting part of this problem, is that heating and cooling in a building, you have these kind of very long timescale things, and you probably even have even longer timescale things where the actual seasons come into play, right? The algorithm, the reinforcement learning agent that you run in the summer might have to be different than the one you run in the winter, and that's a very long time scale for a reinforcement learning agent that might only be, or that might be running at a much faster control loop, right? Something like 10 hertz, 100 hertz, right? And making it aware of dynamics that exists in the kind of years scale is very difficult for a system that operates in the seconds scale. Heuristic-based controllers is what they are comparing this against, right? And that's where I would say that this is kind of a little bit sad, because it kind of shows you there wasn't a ton of juice to squeeze if the heuristic-based controllers were pretty much up to par with the applied RL that Deepmind could offer, right? And you can bet that Deepmind was trying really, really hard to make that number as high as possible, right? So the fact that they were only able to get something like a 10% improvement isn't great, because the return on investment for this is terrible if that's the case, right? 9% energy savings on a warehouse is not worth 10 machine learning PhDs. Okay, so Markov decision process, MDP. This is the standard kind of formulation of reinforcement learning problems, where you have this 5-tuple, right? You make your environment into a state space for S, action space, you have a bounded reward function, you have a discount factor, which modulates how much reward in the future matters, and then you have a transition function, P, in this case, that is the environment that tells you how given a certain action and a certain state, how you will move to a new state. And then the final thing that you actually are creating is a policy, right? This is the entire reinforcement learning problem, is all about creating this policy, which is usually parameterized by a deep learning function approximator that takes in an action, or takes in a state and then outputs an action, right? So the state in this case might be the temperature of a bunch of different buildings and the current situation, or the current status of the different heating and cooling elements in that system. And then the action might be whether to turn another one on or turn something off or increase the temperature on one system and so on. A solution to an MDP is an optimal policy. So yeah, you want to find the policy that maximizes the expected return, which is the reward. T is the optimization horizon, right? You have a discount factor. Action value function and state value function. So these are functions which are parameterized by also deep learning function approximator, so a neural net. And a state value function, given a state, will tell you what the value of that state roughly is, right? So if you have a chessboard, there's going to be some configurations of that chessboard that are high value and some configurations that are low value, which means that in this kind of state, you're likely to lose. In this kind of state, you're likely to win. And the policy is trying to get to these high value states. The action value function is basically just a kind of a take on that, where it says, okay, in this state and taking this action, what is kind of the reward? So it kind of models the value. The action value function tries to give you a quantitative evaluation of how valuable it is to take a certain action at a certain state. Trajectory of length n. Okay, so this is the trajectory. So trajectory is a series of states, actions, and rewards. So this is kind of the interesting part to me, is that, right, depending on what the amount of time between subsequent states is, it's going to be very difficult to have rewards that are very, very far away in time, right? Because then your discount factor here is going to very quickly zero those out. So finding the right discretization of time and control speed for this is going to be difficult, or there's going to have to be some kind of like multi-part reward function. Okay, policy iteration. You can tell whoever wrote this paper was someone in Sutton and Bardot's circle, I suppose, because they just keep referencing these papers. Policy evaluation step estimates the value function of the current policy. Okay, there's two different forms of policy evaluation here. You have TD learning and Monte Carlo evaluation. So a TD learning takes this action value function, right? And Monte Carlo policy updates the action value function this way. So TD learning, this is the function here, right? So you're basically evaluating the function at the next time, right? And at the policy at the next time. So you're saying, here's the value of the next state and whatever action would come out if we were at the next state, right? This is the policy. The policy takes the state and outputs an action, so that you're going to have the state at t plus 1 and also the action at t plus 1 given that state. And then you discount that, right? And then you basically try to get this to match the actual reward. Monte Carlo is kind of the same thing, except you're kind of actually going out and calculating it for all of time step t, right? Yeah, the optimal policy, which is this pi tilde of s, is the action A that maximizes the value function at that state and that action. So there's going to be a bunch of different possible actions at any given state, and you want to pick the action that maximizes the value function. And that's how you know what action to take, is you basically look at the action value, or what's it called here? You look at the action value function and you see which action maximizes the value of that. And the optimal policy is the policy that always takes the optimal action at each time. So that's kind of a little review of reinforcement learning. Okay, and now the paper is going to go into kind of a review of cooling systems. This should be interesting. I don't really know a ton about cooling systems, so let's see what happens here. Schematic diagram of a water-cooled chiller plant with one chiller and one cooling tower. Note that the distinct chilled and condenser water loop. So condenser water loop, chilled water loop. So I think in these type of systems, usually you have separate loops of water, right? You have water moving through a bunch of pipes, and then you have kind of one closed pipe system and another closed pipe system, and they can exchange heat through some kind of heat exchanger or condenser right here, but they don't actually exchange water. So actually, you know what, before we kind of start postulating on what commercial HVAC systems look like, let's just kind of read this section here and then we'll understand it better. Okay, the goal of the HVAC is to maintain the air temperature and humidity. Okay, so I didn't think about humidity. That's interesting. While providing adequate fresh air to maintain indoor air quality. Okay, so there's also like some notion of air quality, and maybe you can measure that somehow with a sensor. The cooling system reduces the interior air temperature by rejecting heat from the building into an external sink, such as the atmosphere, and extracts water vapor from interior air so that it can be removed from the building. Huh. Okay, so there's also like this whole humidity kind of control loop. The total building loop load comes from incident solar radiation, convection from outdoor air, convection and conduction. So convection is whenever you have basically thermal energy being transferred from a kind of solid medium to a air medium, right? So if you have some soup in a spoon and you're blowing on it, you're performing convection, right? The air from your breath is cooling the soup through convection. Conduction is thermal energy transfer from one kind of solid state material to another solid state material. So if you were to take that spoon filled with soup and then touch it to an ice cube, that would be cooling down the soup through conduction. So this is kind of telling you all the different ways that the building is receiving and releasing thermal energy to the outside world. You have convection from the outdoor air, conduction from the ground, ventilation, airflow, air infiltration and exfiltration, so air leaving and coming into the system. Occupant metabolic processes, so humans just heating up. Lighting, computers, other equipment, etc. Measured in tons, which roughly equals 3.5 kilowatt. So I guess that's like the total amount of energy moving in and out, but I assume this is variable over time, right? So maybe this is the peak, the maximum amplitude of the total building load. Due to the variety and variability of building loads, they are challenging to model, but they're possible using physics-based models such as Energy Plus. Okay, so here's the heuristic, or here's the model upon which you can apply optimal control theory to get the kind of heuristic algorithms that they probably were using for decades. The effort to create these models is substantial. In larger facilities, it is common to utilize pumped water and fan-driven air as energy transport mechanisms. Okay, so this is how you move energy around the building, is through basically air in those giant industrial kind of ducts, and then water inside pipes. Chillers, cooling towers, pipes, and control valves. Okay. Typical components on the air side system include air handlers, variable air volume units, fan coils, ductwork, dampers, and diffusers. Chilled water is used to distribute cooling to the section of the building where it is required. Water to air heat exchanger coils. The air cooled and dehumidified air is provided to the HVAC. Okay, so once you've taken that hot air and you've cooled it with the water in this water to air heat exchanger coil, then you need to cool that water back down, right? The water now has all that thermal energy, and you want to get rid of that thermal energy so you can reuse the water, and this is where you have the chiller. Cools the water by rejecting its heat into an external sink. With water-cooled chiller plants, this is typically done using cooling towers, okay, which use evaporative cooling. When the outside wet bulb temperature is not significantly colder than the temperature of the warm bottle, typically using vapor compression refrigeration cycle. So the way that refrigerators work is that they basically use the concept of air pressure, right? So there's a gas has a certain amount of pressure, right? There's a high pressure gas, low pressure gas, and all those in a high pressure gas, all those little molecules are very close together. Low pressure gas, they're very far away. And that actually is a way. High pressure gas, there's a lot of energy in there. Low pressure gas, a lot less energy. And a lot of refrigerators, what they do is they kind of play with that, and they'll take gas that's compressed and then very quickly uncompress it, and that will absorb a bunch of energy or release a bunch of energy. So playing with the pressurization of gas is one way to kind of like suck energy out or put energy into the system. Chiller plant is controlled by the BMS. What is the BMS? Building Management System. Okay, in our case, this BMS was modified to allow for safely switching between obeying its normal heuristic-based controller and accepting alternate recommendations provided by an external agent. So the evaluation of this RL agent is interesting, right? In a lot of RL research, you'll sometimes do it in simulation. It's very easy to control, right? You evaluate 100 times in simulation with controller A, and then evaluate 100 times in simulation with controller B. And that allows you to very directly compare. But there isn't a simulation for this giant building with a building management system and all the kind of intricacies there. So they basically have to alternate kind of A/B test, but where you can only do one at a time. And there's going to be all kinds of complications with that, right? Where maybe if it's a cold day and then a hot day, and you run the heuristic on the cold day and the RL on the hot day, it's going to be very difficult to kind of compare and say which one did better because the environment itself changed, right? I'll take a quick sip. I'm drinking some espresso coffee today. Sequence of operations. Okay, so this is basically just the state machine behind the heuristic controller, which basically, right, you can think of this kind of graph, right, a state machine. You can think of it just in your head, think of a bunch of little circles and squares connected with arrows, and in each circle you have, okay, if the temperature here is greater, then go to this arrow. If the temperature here is less than this, then go to this arrow, right? And there's going to be all these different, what they call set points, which kind of control the flow through this graph, which has been designed by a human. Yeah. The optimal combination depends on many external factors. It's very difficult and time-consuming to design one of these state machines because they're going to be different for each building, depending on what stuff you have and so on. Okay, here they're going to fit the problem into a Markov decision process. So the state is going to be a numerical array of sensor measurement values such as temperature, water flow rate, and equipment status. Here you finally have the time. So this is the time discretization. They're saying 5 minutes. And this will be one time step. Okay. So they finally told us out. It's not... I would have maybe thought that this would have been a much faster control loop. I was literally thinking seconds or fractions of a second, but this is a much slower control loop. We're talking every 5 minutes. So every 5 minutes, you are recording the value for all those sensors. That's your state. You're going to give that to your policy, and the policy is going to output an action, which is here. Action is a 12-dimensional vector of real valued set points available to the SOO, as well as discrete actions for turning on. So it's basically 12 different little switches it can turn on, or little knobs it could tune for the different components of the system, right? So the chiller and all these different parts of the HVAC. The reward is the negative of total energy consumption from the chiller. I feel like so I think the way that they're going to say is that there's going to be a constraint. Horizon T constraint. Yeah, I would have said that the reward should include some notion of human comfort in there, right? It shouldn't just be minimizing total energy consumption. It should also include kind of how comfortable are the humans, how often are you switching things, right? In a lot of these kind of mechanical HVAC systems, there's components there that they have some life cycle, right? You can maybe only switch them 10,000 times before you need to replace them. So minimizing the total amount of switches could also be a different component of the reward function. So I think there's a lot more stuff maybe they could have done here with this reward function. But the way that they set it up is they basically define constraints. So they have a simple reward function and then a bunch of constraints. We use different horizons for the value function and the observation constraints because the affections of act can be manifested at different time scale. Yeah. So this is kind of like one of the age-old problems with reinforcement learning, where if the reward isn't kind of very close to where the state and the actions that resulted in that reward are in time, then it's difficult for the policy to understand that relationship, right? Where this is classic in kind of video games where you have to you have to perform a bunch of actions, and then at the very end you get a reward, right? And the distance in time between that reward at the very end and the actions that you need to take potentially at the beginning make it much more difficult to learn, right? This is why a game such as Montezuma's Revenge, which is like kind of one of the more difficult Atari games that people tried to solve with RL, this is why it was the most difficult, because you had to like go into all these different rooms and like collect a key and then go back to all these different rooms and then touch the door, right? And it's like you only got a reward for getting the key and going to the door, and that's like a very far set of actions and states in order to get that reward. So there's something similar happening here, right? Where once you turn on the chiller, the building might not actually reach the temperature that you want for hours, right? And you're not going to get that reward until much later. Okay, policy improvement with constraints. For each time step T, sample valid actions. Okay, so you have some set of actions that you can possibly take at that time step, and then you're going to look at you're going to go through each of those actions. You're going to predict the mean and standard deviation for energy uses and the objective observation constraint function. So here's your action value function. You're going to feed the current state and then all the possible actions. You're going to get a bunch of different values, right? Here. This is the mean of the energy usage for that action and the standard deviation, sigma, right? So mean, mu, standard deviation, sigma, for the energy uses, and then also the constraint function. And you're going to get however many actions there are. Maybe there's 10 possible actions. Then you're going to evaluate the action value function at each of those. Then you're going to filter out the actions that are predicted to violate the observation constraints. Okay, so yeah, so you're going to have a bunch of actions here, and then you calculated the constraint function mean and standard deviation, and you're going to basically say, I want these to be less than u, whatever u is. I think they'll probably tell us later. And if they're not less than u, then I'm going to throw that away. So I'm going to filter down all my possible actions into some set of actions that don't violate the constraints. Then we're sampling from a uniform distribution. Okay, what are we going to do with this? And then if that sample is above some epsilon, then explore. Okay, This is such a mathematical way of saying that we're going to randomly explore sometimes and then randomly exploit, right? Explore is taking actions that might not be the optimal action for that, but allow you to explore the state space, right? So a reinforcement learning agent, you want it to occasionally try things that aren't necessarily optimal, because sometimes you need to do suboptimal things in order to get to the actual true optimum, right? There's this kind of like local minima versus global minima problem. So you want to trade off between those. You want your reinforcement learning agent to sometimes do the most optimal thing and take the most optimal action, but then sometimes you want it to take kind of a random action, if you want to think of it that way. Yeah, so argmax, this is the action that maximizes exploitation, the optimal action at that current state, and then you have exploration, which is not the argmax. And then finally you say, here's the action I've chosen after going through this whole process, and then you send that to the different the different little systems in your facility, your building management system, and your building management system carries out those actions, and then 5 minutes later, you repeat this entire process. Action value function architecture. The input layers are state action tuples. Okay. Shared layers are shared for all predictions within each tower. The head layers are specific to each prediction. Okay, so you have the state and the action, right? So the state is numerical array. They don't tell us the dimensionality of that, but maybe it's like 100 things. The action is about 12 numbers, so you have 100 numbers and 12 numbers, which represent the state and the action. This is your action value function, so this capital Q. Then you have this kind of like split into different, so it's not just a fully connected neural net, right? It's not every single neuron in this in between is not just fully connected to every other one. You kind of have this separation into towers. So we'll see what that means. Okay, so this is an ensemble algorithm. So ensemble is a French word, and it just means a bunch of things, right? So rather than one expert, you have a bunch of experts. So instead of one person saying what we should do, you kind of have 10 people saying what you should do, and then you can kind of pick the best one amongst those 10. So an ensemble of neural networks is you have multiple neural networks, and each of them predicts their own little action, and then you can decide from those predictions which one you want to do. This is learned from offline behavior policy data. So the learning is happening offline. You're collecting a bunch of state and action pairs in the real system, and then you're putting them in a giant database, and then you're training the policy on those state action pairs. Discards at each time step the actions that are known to violate the action constraint. Okay. Our agent controls multiple chillers. Okay, yeah, I mean, they're just saying that there's a couple of difficulties here, right? So in a data center, you basically have these server farms, and you want it to be the same exact temperature every single day of every single year, right? It's a very simple kind of control objective, versus here, there's going to be a lot of intricacies, right? If there's no one in the building, you kind of don't want to spend a bunch of energy cooling it. So you could almost imagine that the most important thing is figuring out where the humans are in the building, and which rooms don't have humans, and which ones you don't need to be cooling, and so on. And I wonder if they actually even did that, because that seems like right, like how much more difficult would the state space be if you had cameras in every single room and you were keeping track of how many people are in the room, how much furniture there is in a room, maybe to cool it more, cool it less. Like, you can really make this problem significantly more difficult. They call it B-cooler. Right, BVE-based constraint optimization learning with ensemble regularizations. They tried really hard to have the word cooler in there, given that this is a cooling problem. Each day, the current policy is reevaluated using data up to and including the most recent day, and the next policy is produced by policy improvement using the updated queue function. Okay. Some small amount of violation is permitted. So I think that's why that's what this is, right? That's what this U is basically they're saying that you have your constraint function, and there's some value U that says how much are you allowed to violate these constraints. And that's what they're saying here. Small amount of violation is permitted of the constraints. Okay, the policy evaluation steps learns the multi-output action value function, where D is the number of outputs. Right, I think it's 12. Okay, no, the action is 12-dimensional, but this is the output of the action value function. So the action value function doesn't just have a single number, right? It's not saying here's the value of this action at this state. It actually has D numbers, and each of those numbers correspond to different things, right? So you have an energy consumption and one output corresponding to separate energy consumption and a separate output for each of the observation constraints. So it's this part here. Normally, your action value function might just output a single number, or maybe the mean and the standard deviation of a distribution. And here they have the mean and standard deviation for the energy usage, but then they also have mean and standard deviation for all the constraint functions. And you're going to have D total. Targets generated by taking the time normalized average power consumption from T until T plus H, where H is a pre-configured look ahead. This is a modified version of the Monte Carlo target, where this is the discount equals 1. So what does it mean that the discount is 1? So a lot of times, for example, people will say the discount is like something like 0.95, right? And what that is saying is that the reward I get at this step is more important than the reward I get at the next time step, right? By a factor of 0.95. So if I get a reward here of 1 and a reward the next step also of 1, the reward at the next step is only worth 0.95 instead of 1. And then you keep multiplying it out so that as you go further and further in time, the reward at that further point in time is actually worth increasingly less, because you're taking a smaller and smaller percentage of it. But if you say your discount factor is 1, what you're saying is that the rewards are the same, that a reward 50 steps in the future is worth just as much as the reward immediately right now, which I think is a good idea to do here. And they're picking this time horizon H, which they call the look ahead, instead of infinity, which I kind of agree with. That makes sense. We decided to use Monte Carlo targets instead. Okay. Easier to understand for facility managers than discounting? Okay, so they were trying to explain temporal difference to some people at this HVAC company, and they just didn't understand it, so they just kind of went for the Monte Carlo. And then they also pull out this kind of like sentence from this paper saying that finite horizon Monte Carlo is not inferior to temporal difference target, even when the rewards are sparse or delayed. I would say there's probably a context or caveat to that sentence, but I don't know, I guess they did the ablation study, or maybe not. One of the main advantages TD-style methods have over Monte Carlo is the ability to perform off-policy training. However, off-policy training is known to be problematic when RL is used with offline data. So, off-policy training means that you're not using your optimal policy that you currently have, right? You have a little neural net called the policy, and that neural net takes states and outputs actions. Off policy means you're venturing outside of this little neural net's state and action kind of like path, right? And this is great, right, if you're interacting with the environment live, right? But if you're doing it offline, right, so you recorded a bunch of trajectories in this environment, and you recorded those, and now you're training on those, you can't really go off the trajectories in those because you don't know what happens, right? You took a certain action given a state, but you don't know what would happen if you took a different action on that state because you're not actually in the system. So that's kind of what they're trying to explain here. Large action search, there's a big action space, right? So that's kind of what they're saying here. TD style off policy becomes very computationally expensive. So you have a multi-headed neural net. Okay, so all right, so they're kind of explaining the separation here. So they're basically saying that these different heads predict the different parts, right? So this is the action value function, and each of these green dots is one of these different things here. Maybe the energy usage or different constraint functions, right? And they said that these are different enough that you actually want them to be separate heads, right? You want a different neural net that takes the same inputs, but a different neural net with different weights and different kind of things that it's paying attention to output the constraint function versus the energy. So by keeping those separate, they think they get better performance here. In order to give the agent a better understanding of its prediction, we train an ensemble of neural nets. Every member of the ensemble has the same architecture, but is initialized with different weights. Okay. So it's not, sometimes when people do these ensembles, they'll have different neural network architectures or trained on different data sets, right? In order, because you want your ensemble of neural nets to each be different. You don't just want 10 copies of the same neural network because they're all just going to give you the same answer. You want 10 copies of slightly different neural networks so they give you slightly different answers. So here, every neural network, it's the same neural network, but they initialize it with different weights. So whenever they first create the neural network, they initialize it differently. So, and then they also feed it the data in a different order so that at the end you get 10 different neural networks. Even though they have the same architecture, the weights and the biases and the little numbers inside those neural networks are different so that they're going to output different answers. Total of the action. Okay, here you go. Finally, the numbers. Action value function has 62 input features, 50 observations plus 12 actions, and 25 total predictions. One objective plus 24 observation constraints. So the constraints, there's 24 constraint and then one energy. A month of training data has around 10K examples. The model is retrained daily using all data collected up to that day. That's, I don't know, we'll see how much training is going on because that can get expensive. Remaining actions are scored, blah, blah, blah. Okay, so they're basically just describing that algorithm one that we talked about. Ooh. All right, so live A/B tests. This is what we found earlier. So there was a university. And then you had a multi-purpose commercial building. Yeah, changes in the outside weather and building load will significantly change the amount of energy used. One method that we used was alternating daily. Yeah. This is the hard part about kind of an A/B test where you can only run one at a time, where you kind of have to, you never have a direct comparison because the environment is different every time. Okay, they said that they did it kind of August to October, which means that they had cooler temperatures and warmer temperatures, and then they kind of hand wave, and then they say, this means that we will be more confident over the year. I kind of buy this argument, but I also kind of don't buy it. I think that the dynamics in the summer and in the winter are completely different. So, in fact, if I were them, I would have probably waited for the winter because you can probably get way more energy savings in the winter because you're just using way more energy to begin with. AI savings. So, you can see here in August, the energy savings, it kind of spiked real quick. I don't know what happened there. And then it spiked again in September. Oh, the flat region was due to a pause. Okay. Okay, so they're trying to get out of jail free here. They're saying that the heuristic controller, right, was tuned. So they had experts come in and really make it the best possible HVAC controller probably in the world, like just the best possible thing. So this performance or this saving percentage is not against your kind of average run-of-the-mill HVAC. It's actually against a very well-tuned and high-performing heuristic-based HVAC controller. Okay, B-Cooler does very well when the outside temperature is colder and when the load is slower. Okay, that's actually kind of what we were saying. And it doesn't do quite as well when the outside temperature is higher and when the load is higher. One explanation for this phenomenon is when the temperature and load is high, the equipment are running close to their max capacity and there's less room for B-Cooler to make intelligent decisions. Yeah, that's true. So if it's hot outside, the optimal policy is just to run the AC the entire time. And if your heuristic controller is just running the AC the whole time, your AI controller is also running the AC the whole time, there's not a lot of kind of space to improve there. And then kind of this goes back to what we were talking about with having additional parts of the reward function. So you could see how maybe one way to improve in that situation would be to only run the AC, 45 minutes of every hour, where you kind of run it for 45 minutes, turn it off, then run it for 45 minutes, then turn it off. But the problem with that is that constantly turning on and turning off the system, you're going to kind of wear the components more. So you're using less energy, but you're wearing down the components. So there's all these kind of like intricate parts of this problem that I feel like weren't necessarily answered here. But that also means there's a lot of space to grow and improve in this problem space. Okay, each box shows the percent energy savings. Higher is better. So we have here percent savings, WDT, start date. What is WBT? I don't know. Maybe this is outside temperature. So this is like 45 degrees and this is 80 degrees Fahrenheit. Okay, here you go. Outside wet bulb temperature in degrees Fahrenheit. So that's what WBT means. Okay, so we have the percent saving. So actually, interestingly, it drops below. So this pink here at an outside wet bulb temperature of 75 degrees. So when it was nice and hot outside at a load of 1200, the AI system actually performed worse than the tuned heuristic controller. And when it's cold outside, right, wet bulb temperature of 45, 50, 55, cold outside, at a lower load, the AI system performed significantly better, like 30% more energy efficient than the tuned controller. Okay. Applying RL to physical systems. Yeah, this is kind of what we've been hinting at, is that a lot of RL research is done in simulated environments, and there's a lot of stuff that you deal with in real systems that makes it significantly harder than simulated systems. And this is very, very true in robotics, where I kind of have done most of my work, and people avoid the real robots like the plague because it's just so much easier to do things in simulation. limits that can be observed during training. Yeah. This is kind of what we were talking about before, where if you only have a real world system, you can't take actions that you haven't taken, right? You're learning from offline data. So you don't know what would have happened if you would have done something. If you're using a simulator, you can actually see what would have happened, right? You can actually say, okay, well, let me use my simulator to tell me where I would have ended up, what state I would have ended up in if I would have taken this action at this state, which I didn't when I actually did do it. So that's where simulators come in, where you can actually simulate trajectories in state space that you can't do with a real world system. You only have the trajectories that you took. Okay, they have this kind of like the complexity introduced by these constraints. That's kind of where I say that I was saying that you should just get rid of the constraints, just put it all in the reward function, and then just tune the weights on there. Non-stationary dynamics. Yeah, if you recalibrate a sensor, kind of all the historical data on that sensor can be wrong. This happens in robots too, right? Where you collect a bunch of data, then you move the camera position, and then all that data you collected is worthless. Per head feature engineering. That's no good. Training on AI-only data, we favored the richness of the data generated by bcooler over the more static data generated by the SOO. Yeah, so I mean the bcooler is the AI one. So it has this kind of exploitation component, right? Where it's going to sometimes takes actions that are a little bit weird, and you're going to result in more trajectories through this state space, right? More richness, more variability in the trajectories through state space versus the heuristic controller, right? The classic one. It's going to be doing the same thing every single time. So the trajectories are basically they're all going to be very, very, very similar, and that data is kind of stale. It's static, right? It's kind of just 500 examples of the same exact trajectory through state space. Okay, and here kind of a nice little table showing you the different challenges and then the mitigations that they used for that challenge. And that kind of seems like that's what the rest of this paper is all about. Let me take a quick sip here. Okay. So first challenge was just limited data, right? Didn't have a ton of data. It was all offline. You have no simulator. Mitigations they used for that: model unit tests, data examination and cleaning, feature engineering. So this is not great. Feature engineering, data examination and cleaning. This is just basically a bunch of humans in the loop. And not just humans, but like extremely expensive humans, right? Like reinforcement learning researchers working at Deepmind. Complex constraints. Tweaking and hierarchical stuff. So again, the system is kind of complex. There's a bunch of these constraints, and then they come up with this hierarchical heuristic and then manually tune. So for both of these, this is just a bunch of human in the loop type stuff too, so it's not great. Non-stationary dynamics, again, more human in the loop stuff. Inference must happen in real time. Action pruning, this is fine, right? That's an automatic thing. Different operation modes, mode-specific action masking. Okay, so depending on which operation mode your HVAC system is, you kind of mask out certain actions or certain parts of the action space. And then multiple time scales for action effects, hierarchical chiller heuristics. So, okay, they basically just applied a bunch of human engineering and sometimes human in the loop cleaning of data and examining and looking, feature engineering. I don't know, it's pretty rough. All right, for each challenge and mitigation, we point to the section that expands on it. We created a hierarchical policy with heuristics in order to handle actions with different effects time horizons. Actions with longer time horizons were governed by a high-level policy, while actions with shorter time horizons were delegated to a lower-level policy. Okay, so you have a policy that's acting kind of on a longer time horizon, and then a policy that's acting on a lower-level time horizon. Split the policy into two parts. Tweaking the constraint specification. We spent significant time working together with Train to come up with a set of constraints that allows the agent to satisfy the customer's needs. Yeah, so this is the human comfort. They formulated that as a constraint rather than part of the reward. To combat the curse of dimensionality in the action space, we created an efficient way to prune and search through the action space. Okay, so you have very high dimensional action space because there's potentially a ton of these different chillers and coolers and pumps, each with a bunch of different knobs that you can turn. So you want to be able to prune through that, and I think that's the constraints, right? And that's what they do here, mode-specific action masking. So depending on the current state of the environment, you take the full action space and cut it down, right? So if you're in the winter, you mask out all the parts of the action space that are related to the AC, right? And you're only messing with the heating stuff and so on. And I think this is a good idea too, right? Because you can imagine how an AI system might try to use both, right? It might try to become clever and say, okay, well, I'm running the AC and the heater at the same time, and I'm kind of like alternating them or doing some kind of tricky stuff, and that's something that's just very obviously a wrong idea. You kind of only want to be running the AC or only want to be running the heater. So masking the action space based on the weather outside or kind of the environment is a clever way to kind of simplify the action space. We spent significant time ensuring that the data was of high quality. Yeah, I think this is just generally the case for any kind of machine learning. You have to kind of examine and clean. Two main sources of data, historical data and data collected by bcooler. Historical data is less than a year. Facility data from the SOO controlling. can be thought of as a behavioral data set from an expert policy. Yeah, so this is kind of what we were saying, that the SOO, which is the heuristic controller, it's gonna be doing the same thing every time. So your trajectories are gonna be the same through state and action space. So it's difficult to learn a good action value function from that. Yep, the AI control data contains rich exploration data that spans a wide variety of actions and states. Yeah, I would say that the solution to this is actually simulation, right? I would say create a bunch of virtual systems and simulation with different sizes, different types of domain randomization is the word for this, right? Where if you have a legged robot and you're training it to walk, train this policy on a huge variety of legged robots in simulation that have different size legs, different size bodies, and then the optimal policy for all of those variations in simulation will actually adapt to the real world system somewhat well, right? And this sim to real problem is definitely still not solved, and there's definitely techniques there, but I think you could probably do something for this, right? Where you have a bunch of fake warehouses in the simulated world, and then a policy that learns from these fake warehouses can be kind of applied and instantly start working in a real world system. One major difficulty is translating the system constraints known by the facility manager to a language that BCooler can interpret. So there's 59 different constraints on the action space and 24 constraints on the observation space. You can tell whoever wrote this paper was kind of sour about dealing with the facility manager. First, they were kind of shitting on them for not understanding temporal difference learning, and now they're shitting on working together with them and overly complicated constraints. Measurement age. Okay, so this kind of shows you that different parts of the state space and action space are going to change, right? There's a kind of a fundamental shift over time of the distribution of kind of the actions and states, right? So in kind of the early parts of the experiment here, you were in these blue points here, but later parts of the experiment, you were in these red and yellow points. So the distribution shifts over time. Learning limited. The environment that the agent is non-stationary, it changes. The distribution shifts over time. Chiller plants, the chiller's capacity degrades over a time scale due to fouling. Yeah, so you have these kind of non-smooth dynamics in the system, right, where the chiller will slowly become worse and worse and worse and worse over time, and then suddenly it'll just improve very quickly because it gets cleaned. And that kind of non-linearity in the dynamics of the system is very difficult to adapt to in a reinforcement learning system, which is why I think that if you do this in simulation, you can simulate this type of sudden change in the system, and your policy will become more robust to it. The control needs to happen in 1 minute. I would say that's actually pretty easy. Right, I think 1 minute is more than enough time to send a request to a Deepmind server, which evaluates and gives you the action. Okay, you have different modes with different action spaces and constraints. And they do this masking, right, where the agent has all actions available, and then they just mask out the actions that don't correspond to a particular mode. Prod default. Comparison of models on selected individual unit tests. We see that the models with multi-tower architecture agrees much more with the expected results than the standard multi-headed model architecture labeled default. So this is the temperature down here, and then you have max. Okay. I guess prod is the heuristic controller, and then, or no, expected is the heuristic. This is what you actually wanted. This is what the human does, or the human expert would do in the situation. And then all submodels is with the multi-tower architecture. So they did do the ablation. The ablation that we were talking about, where you split either you split the model early and you have these multi-towers, you have different towers within the model, or you split the model late, where you have a giant kind of feature block and then you have just little thin heads. And you can see that the separate towers are better in the sense that they're more similar to what the human would do, or the expert. Yeah, this is the problem. It's like all supported by domain understanding and thorough analysis of historical data. Like the same way that you can overfit in machine learning, you can overfit to the problem itself. And the more time you spend inside a problem, the more time you can engineer and design subcomponents of the system specific to that problem. But I would say that if you're doing kind of research and you're trying to solve the general problem, the over-engineering for the specific test problem is actually not great. And you can kind of feel the tension in this paper and in this work where the final result isn't that amazing, right? A 10% improvement in performance or in energy consumption is not huge. And then you go into the paper and you realize that they did a ton of hard-coded engineering and kind of data cleaning, domain understanding, like all this stuff, right? It's not like they just threw all of this into one giant transformer and then it increased energy savings by 300%, right? I think that's kind of what they wanted. They wanted to kind of get like a big bang with a very generic, simple system and architecture, but instead they have a very complicated, convoluted, domain-specific kind of system, and it doesn't actually perform that well to begin with. We ended up with a large set of auto-generated individual model unit tests. We decided to come up with one aggregated metric by computing the normalized mean average error for each relationship. No submodels with submodels, okay. So this is the split early versus split late in the neural network architecture of the action value function. Feature selection significantly improved the model's performance on unit tests. Yeah, I mean, humans are good. Yeah, so what does feature selection mean in this case? It's basically that the observation space, right, they said earlier was 50, but actually the true observation space was 176. So they filtered that down. This is the actual final architecture that they use, right? Multi-tower, multi-headed MLP, multi-layer perceptron. Yeah, so basically it looks like there's like the number of pumps that you're running is actually quite important. And then if you look at the heuristic policy, it kind of always ran the same number of pumps probably. So they trained it on, they didn't use that historical data from the heuristic policy to train for that reason, right? Since the heuristic policy is a static policy, the strong correlations didn't allow for the model to disentangle the effects of this action. You need to explore, you need rich and variant you need a rich variety of states and actions in your data in order to train a good reinforcement learning agent. Yeah, so this is, we were talking about this at the very beginning. There's kind of dynamics in this system that are longer, right? You have things that are, the system is really looking 5 to 15 minutes ahead, but then you have these dynamics of that are kind of much longer in the hours, potentially even days, you know? So they ended up having two different policies. There's a number of chillers And then, okay, so they have a heuristic that picks the number of chillers, and then the actual agent is just then choosing the actions corresponding to that number of chillers. Yeah. I wouldn't even call this a high-level agent, though. This is a heuristic. And here you go. They're shitting on the facility managers again. You can feel the tension in that relationship, which must have been pretty weird, right? You have a bunch of super academic Deepmind researcher people interacting with facilities managers at like a shopping mall, right? And that's just kind of two people from completely different worlds, and you can just kind of imagine what the conversations were like, and the tension, and kind of the disillusionment from the facilities managers once they realize kind of how much hard coding there is, and maybe how much they probably had all these expectations of the AI cooling being so much better, and maybe they had some fear, right, where they thought that maybe the AI cooler was going to take their job, so there's the kind of whole automation aspect to it. So it's very interesting to kind of think about what that relationship must have been like day to day. Okay, so there's a lot of possible actions that you can generate. So they cap the number of generated actions to 100K. And then the mode-specific action masking. Missing data. Yeah, so the system itself is just a mess. Only evaluated in simulation. I would say that's where you're going to get the actual optimal policy that would apply to a variety of different environments, rather than just an optimal policy that works for this one very, very specific system. Offline RL. Okay, a natural approach to offline learning is to downgrade the value functions for state action pairs that have not been seen very often in the offline dataset. So you have your action value function, you have your state value function. In this case, state action pairs are individual states that you're in the environment, and then the actions that you took in that state. And it's saying that if you have an offline data set and you have a state action pair that very rarely occurs in that offline data set, make the value of that lower, right? I guess maybe in some situations, right, you can have one example in an offline data set where you have kind of a high reward for a specific state action pair, but it only happens once. And in that case, actually, you want that reward to be kind of, you want to lower that. You don't actually want to go there because there's a reason why you haven't been into that state very often. I don't know, maybe there's like kind of a safety angle there. Our approach of penalizing by the standard deviation of the Q value can be seen as an example of this type of approach. Since state action pairs that are frequently seen in the dataset should have lower ensemble uncertainty than rarely encountered ones. Okay, so it's about the uncertainty. Cool. All right, let's see. Conclusion. In this paper, we outline the work that was done by applying RL control to multiple commercial HVAC facilities. No off-the-shelf RL can work in a plug-and-play fashion. Significant domain understanding was required for many of the modifications made. Adding additional domain-specific inductive biases, right, such as the physical topology. So giving the, having the state space, right, the observation space, not just be limited to the reading of the temperature sensors, but also some notion of like where those temperature sensors are relative to each other. So the physical topology of the actual facility. I think that's a good idea. I think this here is the best idea. Build simulations of different facilities with a variety of attributes and use this to transfer knowledge to agents that will be deployed to. So this is exactly what we were describing, right? Transfer learning or direct sim to real transfer. Boom. That's the word we were talking about. I think this is the actual way to do it. This is the actual way to solve it. You don't want to be doing all this like super specific domain specific crap for a single facility. I think you want to figure out a way to create hundreds of thousands of variations of facilities in simulation and then train one policy that can then be directly transferred to any facility. Yeah, large-scale impact requires deployment to new facilities without significant engineering per facility. HVAC simulator. We have some stuff here. Accounting for sensor miscalibration. Another was correct the fact that certain sensors fell out of calibration. Cool. So that's that. That's controlling commercial cooling systems using reinforcement learning. This is a Deepmind paper. I think my overall take on the paper is that it's a little bit of a disappointment. I think they tried a little bit too hard to do everything on the real system. They didn't leverage simulation and domain randomization enough. I think a lot of the different tricks and modifications that they made to the reinforcement learning methodology are specific to this exact system and facility. And ultimately, the energy savings weren't that impressive, which kind of makes a case, doesn't make a good case for the application of reinforcement learning to HVAC systems. I think if this amount of effort really only saves you a small percentage, I don't know if you're going to be saving a ton of money, right? There isn't a lot of squeeze, a lot of juice to squeeze, as I said before. Warren Buddy Bryan. I've never seen that before. I've never seen someone have a name or a nickname, like a fighter name. Interesting. Cool. So that's been controlling commercial cooling systems using reinforcement learning from Deepmind. Thanks for listening, and see everybody later.